All right, another topic with energy. We've gone pretty far with energy. Some definitions for energy, some amounts of energy, and some energy accounting. We can see the energy. You watch things now, you kind of put on your energy sunglasses. Kinetic and potential energy, there, kinetic and potential energy. Up here with my hand, it's rubbing, so there's some energy being lost in the jiggling energy of thermal. One thing that we use energy a lot in a variety of sciences and engineering. It's just a great tool. And again, it's a lot easier than kinematics and force analysis often. One thing that we'll use a lot is potential energy curves. So potential energy we'll see as a function of x. We're going to exploit this more and more. We're going to see it when we get into rotations, and we'll see it a lot in quantum mechanics, a lot. So it's not too bad. Let's start out with the basics, and then you'll have the idea when we get into the more difficult. We're going to show a potential energy curve on an energy versus position graph. So you've noticed that position is a factor with potential energy. And we're going to be talking about this mechanical energy that we talked about. Okay, so let's just, you can read more about it. But this is very useful, and this is a basic introduction, so don't overthink it, okay? But feel free to ask questions. So we're going to look at the case of conservation of momentum, conservation of mechanical energy, if that works. In other words, the object, as it goes back and forth, won't be losing or gaining any, I'm not going to be hitting it, it's not going to be rubbing on anything, any energy, mechanical energy. Remember that mechanical energy is the kinetic energy, all types of kinetic energy, and all types of potential energy. But again, for our case, kinetic energy is just 1/2 mv squared, translational kinetic energy for now. Potential energy, we'll pick a certain potential energy function, anything that can be written like this. Again, don't worry too much about that modeling. You'll get into this as you progress. So let's go over here and take a look at this curve. All right. So I've drawn a curve here, I've drawn a graph. And oftentimes this graph is labeled U versus X. I've used S for a spring, for the amount compressed or stretched for spring. X is fine. And that's misleading. This axis is an energy axis. It's the mechanical energy. And if energy is constant, then I've got a certain amount which I can draw here as at any level. Okay, so I can say, for example, here's my spring, and I could stretch it a certain amount and let it go back and forth. And notice what happens. If I, for instance, stretch it this amount, if the energy is here, then I got an energy equal to a constant. Well, what's happening? Well, I stretch it out and I let it go. So is there any kinetic energy? No, remember that energy is K. Let me draw it this way. I'll use some color here. Kinetic energy, which I'll show you, plus the potential energy. Okay. The potential energy is on that curve. Now, if I've only got this much energy, 10 joules, 100 joules, 1,000 joules, whatever it is, if I've only got that much energy, I can't have more potential energy than that. Right? Again, think 100 joules. I got 100 joules. I can go up to, if the potential energy curve goes up there, that doesn't apply. I've only stretched it out this far. Right? So this value right here, at that moment, it's all potential energy. Okay? And I've stretched that out here. V is 0. We call that the turning point. And I let go. So it's all potential. It's got the potential for kinetic energy. As I let it go, it's going to speed up. Notice that the spring will be stretched less. So I've got less potential energy. And of course, the value of that curve is the potential energy. But I still have the same total energy. And so that curve is also telling you something else. The potential energy plus the what? Kinetic energy is equal to that. In this case, K is 0. Here, you've got more kinetic energy, less potential energy. As that object moves forward, moves in this way, we're getting less stretch, so less potential energy, and more kinetic energy. It goes faster. And then as it passes through equilibrium here, boom, it's going to be all kinetic energy. But notice that the sum of K plus U is that blue line, or the constant total energy. And as it comes back over here, it's going to start compressing, giving it, again, more potential energy. It doesn't matter whether it's compressed or stretched, I still have potential energy, potential for kinetic energy. And as it comes over here, I'm going to slow down, and I can see that here. I don't see a kinetic energy curve here. I couldn't draw that, which is interesting. And then it's going to stop, right? Because the potential energy, the energy is going more potential, and now all potential. And then it goes back, more kinetic, less potential. No potential energy, all kinetic, and so on. What happens if I stretch it out more and release it? Well, then I'll get a very similar sort of thing, but then I'll start out with this much energy. And that much energy, blue line, E equals the constant. And then I'll go back and forth between these points, again, trading off, transforming between kinetic and potential energy as it goes back and forth. Not allowing for any friction in this case, or else it would die down. We'll get to that later when we do oscillations. Okay, so that's how that curve works. Now, remember also, though, one important thing is that I get to choose where energy is zero. So rather than H equals 0, I should have an E here. I could set where E equals 0, and it doesn't make any bit of difference. The spring isn't going to go, oh, I got to behave differently, right? The energy where energy is 0 is a chosen reference. So let's go over here. So we start abstracting this a little bit and taking a look here over at some other curves. The sorts of things you look at in atomic physics, quantum mechanics, or any variety of things. You see this with material science. Conduction bands, semiconductors. So these curves come up a lot, and they're not too bad, so very useful. You see, if this is the mechanical energy, and this curve here then is my potential energy curve, as a function now I've used x as my variable over here, then I see this curve, and I can look at it and go, okay, well, for some reason you've set that to be my zero energy. Again, you can shift that. It doesn't matter. It makes no difference whatsoever. It's useful for some things. And the way we can look at this is not just like a spring actually moving it, but we can get an intuition. If you imagine a ball, if you take a ball and you were to roll it and let it roll, right? If I release it here, is it going to make it over the hill? Well, yeah, it'll roll. What'll happen? It'll pick up speed, pick up kinetic energy, and it'll slow down. But I started up here, so it's going to be able to get over this. If I start here, I'm not going to be able to get out, am I? It's what's called a bound state. So what matters in terms of what happens is going to be how much energy you start with. If I start with this energy, well, I'm going to stay with that much energy. Now here's an interesting thing. This is the total energy, right? Which in this case is negative. That's fine, it doesn't matter. All that matters is the change. So that's how much I start with. Where can I be? Well, energy is kinetic plus potential. If the green is the value for the potential energy, then where is the kinetic energy? Let's try this. Let's say this is negative 50 joules. And let's say that's negative 30. Okay, what got this? This would be negative 50 joules. And let's say that's negative 30 joules. I'm just making it up, right? Well, then what's my kinetic energy? I got negative 30 joules, don't forget the J, don't be sloppy with that, is equal to K plus a negative 50 joules. Of course, you can just write that. So how much is K? Add to both sides, and K is positive 20 joules. So where do you see that? Well, you see it right here. This value here, the difference in there. Okay? So you can still see a K, but it's just like if you took a ball and you released it, all potential energy still speeding up, slowing down. Potential energy goes more to kinetic, more potential. Kinetic and potential trading off. So you can do a bar chart where you show kinetic is high, potential is low, potential is growing, kinetic's decreasing, however you want to do it. Now if I start out up here at 0, well then clearly I could go back and forth like this, but I still couldn't get over that hump. If I start out right here, I'll just be able to get over the hump, and then I'll get down here and I'll be able to get up to, well, just right there. And then it would slosh back and forth. So it's kind of cool how this shows that. Just keep in mind that what we're really graphing is E mechanical, which is often not drawn on this axis. This actually should be the E mechanical. The curve is U, and the difference there, E minus U, is the kinetic energy. This one's a little trickier because of the negative. So if you get confused, just throw some made up numbers in there and straighten it out. I mean, in this case, I've only got X being positive. For atoms, often this is the radius out from the center. Notice here too, that no matter how much energy I have, I don't seem to be able to go over there, according to that curve. It's asymptotically approaching 0. So, whatever that means. And if that means inside the nucleus or inside an atom, lots of different models, okay? But sometimes you'll have the X go this way, and again, sometimes you'll have the curve down here, and sometimes you'll have it up here, and sometimes it'll be modeled as square, even though there's no right corners really in physics, but they get pretty close, so we can do things like that. Neat curve. Now, one last thing that I wanted to mention about these curves is that, well, it's a graph. So it's energy versus position, X or S or whatever. So I can look at a graph, I can look at the points on the graph, the values, and this one's kind of interesting because I can look at that difference because the sum is equal to the total there. But I can also look at the area under the curve. So mathematically, if you gave me a function, I could go, hey, I could do this. I could take the area under the curve, u, x, dx. What would the units be? Let me just explore this. And that's from some earlier state to some later state, right? It's not at an instant, right? But that's x at that earlier state and x at the later because I'm integrating over position. What was that? That's a joule times a meter, and that's a Newton times a meter times a meter. And Newton, well, F net causes MA, that's kilogram meter per second squared times a meter, meter cubed. Just because I can do it mathematically doesn't mean it's useful in any physical sense. All right, fine. What about slope? Let me look at the slope. Slope. How could that be? Let's see, that's a d derivative with respect to x at some x value. Okay, let's get rid of my integral. I don't see much use for that right now. I could explore that, right? Well, again, the units. God, in joules per meter, that has units, right? And that's Newton meter per meter. Hey, that's a Newton. Force. Well, let me explore this. The force. So the slope has units of force. It doesn't mean it's right, but it's getting there. Let's check it out. Okay, so the slope here, well, let me try this. Check this out. What if I take the spring? What if I take 1/2 kx squared, the spring potential energy, dx? What's that derivative equal to? Evaluated at some particular value. Oh, that's kx. That's like the spring force. Huh. But the spring force is negative. So the spring force looks like that, but that's positive, so I got to go like that. Now wait a minute, could it be? Let's see, the slope here at any place is a negative slope. The force here would be in the positive direction. So it would make sense that it is the negative of the slope direction. What about over here? The slope is positive. But the force over here is in the negative direction. So this force is in the negative slope direction. It works. And we're going to explore that later and issues of different types of equilibrium. Stable, neutral, and unstable equilibrium as we get into rotations. Just wanted to hint that this is a pretty useful tool. Not so bad now, but you just, pause. Sometimes it gets a little tricky. You put in some numbers. K plus U is E. All right, that's it for this one. We're going to go on to collisions next.